welcome everyone. Our today's speaker is Michał Pilipczuk, who is going to tell us things about reducing randomness in isolation lemma on decomposable graph. Michał, the screen is yours.
Okay, thanks a lot. I hope that you all see my sort of slides. So I will be talking about isolation lemma and reducing randomness, the amount of random bits that we are using in it. And this is a joint work that we did over the last, let's say, 1 year together with Jesper Nederlof, with Salim Svenhus, and with Karol Węgrzycki. Good. So most of the talk I will actually spend on talking about isolation lemma and why it is why it is interesting and what we can do with it. And in the second part of the talk, I will talk a little bit about our results, but not maybe that much into the details. Okay. So first of all, what is isolation lemma? So this is a very nice randomized tool for the design of algorithms and not only. And on the combinatorial level, it is also very interesting. So the setting is as follows. So imagine that you've got some universe U. Here it is. So it has some elements. It is a finite universe. Yeah. And over this universe, you've got some family of subsets. Usually in the algorithm application, you actually don't know this family. You want to actually say something about it using some random sampling in this universe. Good. So you've got some family of subsets of the universe. So now you can imagine that you can, to every element of the universe, you assign a weight. For instance, this guy will be having weight 1. Maybe this guy will have weight 4. Maybe this guy will have weight 5, and so on and so on. Yeah. So each element receives a non-negative integer weight. So then every subset of your family also receives some weight, which is just the total weight of the elements of the subset. Right. So now you can look at this multiset of all the possible weights of the elements of your family. Yeah. So for every subset from your family, you count what is the total weight, and you look at this whole distribution of the weights. So I will say that this weight function isolates my family if among these weights that I get, there is a unique set that has the minimum 1. So for instance, if I assigned to every vertex, to every element of my universe weight equal to 1, then my weight function would just count the cardinality of the set, and then the family would be isolated if and only if there is a unique set of minimum possible cardinality in our family. But obviously, if we assign different weights to different elements, these subsets from my family, they get distributed somehow with respect to those weights. And if there is a unique one that has the minimum possible weight, then we say that the family is isolated by our weight function. Okay, so far so good. This is just a definition. And the interesting thing about this notion is that if we choose this weight function appropriately at random, then with high probability we achieve this isolation property. Namely, we've got this isolation lemma. This is a result from, I think, late 80s from Mulmule, Vazirani, and Vazirani, which says the following. So suppose that we've got this setting as we had, and the family F of subsets is non-empty. Yeah. Then I claim that if I draw my weight function uniformly at random, where every weight is drawn between 1 and c times the size of the universe, so some constant times the size of the universe, and all the weights are drawn independently. Yeah. So first I flip a coin, c times n-sided coin to determine the weight of the first element, then of the second element, and so on and so on. Then actually, with very high probability, my family will actually be isolated. So in other words, the probability that it will be isolated is at least 1 minus 1 over c, which translates to the probability of not being isolated 1 over c. Yeah. So if I put c equal to 100, then with probability 99%, I actually draw at random an isolating weight function. Good. So this is a classic tool. Maybe some of you haven't seen it before, so I will show you quickly the proof of this lemma. And I will show you the proof not only because the result is important, but also because the proof is really, really nice. It's a beautiful piece of combinatorics. Good. So suppose for a moment that f is not isolated by our weight function omega. Yeah. So what does it mean? Oh, well, this means by just definition that there are two elements of my family, say A and B, two sets in my family that receive the same weight. Yeah, so receive the same minimum weight. So the weight of A is equal to the weight of B is equal to the minimum possible weight from my family. Yeah, and these two sets are different. Yeah. So then I know that if they are different, there is some symmetric difference. So let's take an element of my universe from the symmetric difference, say from A minus B, like the taking from B minus A is a symmetric thing. Yeah. So now I have fixed some element on which the two sets A and B, yes, they differ. Now taking this element naturally divides my family into two subfamilies, say F plus and F minus. Yeah? F plus are all those guys that contain my element E, and F minus are all those guys that do not contain my element. And clearly B belongs to the second one, yeah, because B doesn't have E, and A belongs to the first one. A belongs to F plus. So now clearly, if A was a minimizer, so a set with minimum possible weight for the whole of F, then clearly it is also a minimizer for F plus, yeah, because this is just a smaller family, right? And the same, B is a minimizer of F minus. Yeah. So the fact that their weights are equal, yes, I can translate to the following thing. So here, let's look at this equality drawn on the right-hand side. Yeah, on the right-hand side, I've got simply omega of B. Yeah, this is the minimum possible weight of a set from the family F minus. And on the right-hand side, I've got this is equal to the weight of A, so the minimum possible weight of F plus, and I can write it as the weight of E plus the minimum possible weight over F plus of the elements of F plus with E removed. Yeah, because all of the elements of F plus, they contain E. Yeah, so taking a minimum over F plus of the weight of X is the same as taking the minimum possible weight over all of the weights of X minus the element E, and adding this E on the side. Yeah, because this E is always the same there. It always contributes to the weight of all the elements from F plus. Good. So if we now have this equality here, yes, I can rewrite it to put the weight of E on one hand side. Yeah, so I can express the weight of E as the difference of these two minima. So far so good. We don't see so far where this exactly leads, but we will see this in a moment. Right. So if we have this equality, then I can write that the element E of my universe I will call singular if exactly this happens. Yes, if exactly the weight of E is equal to this difference of minima. And clearly the reasoning that we have just discussed shows that if my family F is not isolated by my weight function, then clearly there is a singular element for my weight function, right? Because, well, if it's not isolated, then there are some A and B that receive the same minimum possible weight, and then any element of their symmetric difference is actually a singular element. Good. So now I claim that actually the probability that a particular element becomes singular is really, really small. And here in this observation is the main point of the proof. So let's look at this value on the right-hand side. Yes, the right-hand side. Now it will become clear why I have put this value on one side of the equation. This value is actually independent of the weight of E. Why? Well, if I take the minimum of the weights of sets X over F minus, yes, then all these sets do not contain E. So clearly this minimum doesn't depend on the choice of omega of E. Yeah, doesn't depend on the choice of weight of E. And similarly, if I look at this one, yes, I here explicitly remove E from consideration when computing the weight. Yes. So also this value is independent of the weight of E, right? So this whole value, yes, this is a random variable that that depends only on the weights of all the elements apart from omega of E, yeah, apart from the weight of E. So then you can think of this probabilistic space as first drawing at random all the weights of all the other elements other than E, calculating this right-hand side of E, and then finally drawing at random the weight of E. Yeah, and then you hit exactly this value right-hand side of E. Well, with what probability? You have some fixed value. Omega of E is drawn uniformly at random from all the numbers from 1 up to C times n. Yeah, so the probability that you hit this particular value is at most 1 over C times n, right? So this happens for every element separately, and then you can apply union bound to argue that the probability that there is at least one singular element is at most, well, this 1 over C times n for every particular element to be singular times the total number of elements, which is 1 over C. Yeah. So the probability that there is a singular element is at most 1 over C, and therefore the probability that that my family F is not isolated is at most 1 over C, because not isolated entails the existence of a singular. Good. So this is the proof of the isolation lemma. Are there any questions about this proof? Okay. If not, if you would like to interrupt me with any questions, please feel free to do it. Good. So this was a very nice combinatorial proof of the isolation lemma. So let's now look at some applications of it in algorithms. So the original motivation of Murmule, Vazirani, and Vazirani was to design randomized algorithms for the maximum matching problem through the, let's say, determinant approach. So encoding the existence of a perfect matching through non-zeroness of some determinant. And these are randomized parallel algorithms. So during this talk, we'll be mostly interested in sort of different applications, namely that that were designed by Tsigan et al. In 2011 for the technique of cut and count. So in particular, one of the main results of this paper about cut and count is a 4 to the 3 times polynomial in an algorithm for the Hamiltonian cycle problem. Yeah, so when I have a graph of 3 at most t, I can decide whether this graph has a Hamiltonian cycle in randomized time 4 to the t times polynomial in n. Okay, so let's. I will not go into the details of this algorithm, but I would like to show you how isolation lemma works in this context. So let's see how it looks. So the naive dynamic programming for Hamiltonian cycle on bounded 3-width graphs, it has running time roughly 2 to the order of t log t times polynomial in n. And you probably, if you had some course in parameterized complexity, you probably designed this algorithm during some tutorial. The key fact is that whenever you have a bag of a tree decomposition, the state of the dynamic programming tells how many edges of the Hamiltonian cycle you have already encountered in the subgraph below, incident to every vertex of the bag. So, for instance, this one has 0, this one has 2, and these two guys have already seen one edge incident to them from the Hamiltonian cycle. And then what you need to do, a partial solution looks more or less like that. Yeah, it is a one or more paths that connect guys with value 1, yeah, that have only one incident edge. And then you need to, apart from this mask 0, 1, 2, for which there are 3 to the t options, you also need to know the matching between the ones because you need to know what is connected to what in order to ensure that at the end you close exactly one cycle and not more than one cycle. Good. So because of remembering also a matching on the vertices of a back, we've got this factor 2 to the order t log t in the number of states. And cut and count was mostly about removing this log factor here. Yeah. So the main trick of cut and count is to observe that instead of deciding whether there is a Hamiltonian cycle in a graph, we are actually counting we can actually count the number of Hamiltonian cycles modulo 2. Yeah. So deciding whether there exists a Hamiltonian cycle, the naive dynamic programming works in this running time. Yeah. But if you want to only count modulo 2, the number of Hamiltonian cycles, then using some canceling tricks, you can actually do it in 4 to the t times polynomial in n. Yeah. So actually, it is easier to count modulo 2 than to decide non-zeroness of the number of Hamiltonian cycles. And even you can extend this algorithm to count the number of Hamiltonian cycles of some particular weight, modulo 2, assuming that the edges of your graph are weighted. Yeah, so edges of the graph are weighted. This naturally gives you a weight of a Hamiltonian cycle, and then you can decide, you can count the number of Hamiltonian cycles of this particular weight in this running time. Good. So what is the algorithm using isolation lemma for Hamiltonian cycles on bounded tree with graphs? Well, we sample a weight function on edges. Yes, a weight function that is polynomial bounded, say that bounds are from 1 up to 2 times m, the number of edges at random. And then for each possible weight from 0 up to 2 times 2m squared, this is the maximum possible weight of a Hamiltonian cycle that can appear in this graph. We just compute the parity of the number of Hamiltonian cycles of this particular weight. And if any of the outcomes is odd, yes, means that the parity of the number of Hamiltonian cycles of this weight W is odd, yeah, then clearly there exists some Hamiltonian cycle, so we can answer yes, and otherwise we answer no. And you can easily see that this algorithm indeed is a one-sided error randomized algorithm, because what happens if there is no Hamiltonian cycle, then clearly all these numbers are zeros or they are even. So for sure we will answer no. And if there exists a Hamiltonian cycle, then the family of all Hamiltonian cycles is isolated by our weight function with probability at least half. Yes, and therefore one of those buckets will contain, one of those buckets where I bucket the Hamiltonian cycles according to their weights, has exactly one Hamiltonian cycle there, and one is odd, and the counting modulo 2 algorithm will actually give me that the number is odd. So I will actually answer yes with probability at least half. Good. So this was basic application of cut and count using isolation lemma. And of course, the main technical thing that I did not tell you about is how to count the number of Hamiltonian cycles modulo 2 efficiently. But this we will not go into the details. Okay, and clearly this algorithm is randomized because, well, I needed to sample a weight function and hope for the best that it will actually isolate my family. Good. So since the introduction of cut and count, there are multiple the randomizations of cut and count using determinant approach, so essentially Kirchhoff's matrix theorem, a rank-based approach, understanding that the solutions in some sense are highly linearly dependent, or you can also think of it using the framework of representative sets. But however, all of those approaches somehow circumvented the problem of the randomizing cut and count directly, let's say. So let's try what would be the naive, the randomization of cut and count. Okay, so we've got our isolation lemma, yeah, and my isolation lemma uses some R random bits, yes, to sample this random weight function. Yeah. So instead of sampling a random weight function and trying just for it, I could just go through all the possible 2 to the R choices of the random bits, yes, and verify one by one all the possible outcomes of the random experiment. Yeah. So the original isolation lemma, well, we have actually here it should be M, because we are, for every edge of my graph, I am drawing a random weight. Yes. So from 1 up to M. So in order to how many random bits I need to do this random experiment? Well, M log M, yeah, because we are using log M random bits for each of the M weights that we are drawing. Yeah? So just a naive randomization would give us running time 2 to the order of M log M. Yes, which is really, really bad. Yes, so definitely you could just any algorithm for the Hamiltonian cycle problem could solve this problem much faster than M power M. Yeah, this can be slightly reduced to the order of M random bits, but this doesn't help us too much. Good. So this is a very naive approach, right? Go through the whole probabilistic space. However, observe that we are not working with an arbitrary family of objects. Yeah, we are working with family of Hamiltonian cycles in a graph of bounded truth, right? So maybe we can somehow use the fact that we know more about the family that we are working with in order to reduce the number of random bits we are using for the isolation lemma. And this brings us to the main question that we asked ourselves at the beginning of the project. Can we reduce the number of random bits in the isolation lemma, provided we know that we have some well-behaved family of objects? Yeah, this F is some well-behaved objects in a graph, say, of bounded truth or of some other bounded parameter. Yeah. And the answer that we give in this work is that to a large extent the answer is yes. And to a large extent means not to an extent that would actually give us a full de-randomization of cut and count, but to an extent large enough for it to be interesting. Good. So what are our results? So first of all, the result that I would like to sketch to you in the remaining 20 minutes is that for the Hamiltonian cycle in graphs of truth at most t, we can make an isolation scheme that uses roughly this many random bits. So there's a factor log square n here, yeah, order of log square n, plus t log n. Yeah, so of course, if t goes to n, this goes to n log n random bits as in the original isolation lemma. However, observe that for t equal to being a constant, so say for a graph of true with t, we've got a isolation scheme that uses essentially log square n random bits. So very, very small number. So you can actually go through the whole probabilistic space in quasi-polynomial type. Yeah. The drawback is that in the original isolation lemma, we were using polynomially bounded weights. Now the weights will be bounded by 2 to this number of random bits. Yeah, so I will actually, in say graph of truth at most t, these weights will be quasi-polynomial. Yeah. So then you can extend, there's nothing too special about Hamiltonian cycle in this theorem. You can actually extend it to any MSO definable problem. So whenever you have a MSO definable family of objects in a graph, so say you've got some formula phi that takes one, say, h variable, you can define a family of objects selected by this formula. So for example, if my formula phi would say this set of edges forms a Hamiltonian cycle, then this family would consist of all the Hamiltonian cycles in my family, in my graph G. So this is a way of selecting a family of objects in a graph. Yes, and for every problem that can be defined using a MSO2 formula, we can give an isolation scheme that roughly uses that number of bits. Yeah, so you still have this factor log square n, and then the difference between the first theorem and the second is that the dependence on true width is some computable function. Again, the weights are bounded by exponential in the total number of bits. So these are our two say main results here. And we give, say, 150 other theorems of this kind. So we are looking at different problems, like independence, different parameters, mostly tree depth, because there you can do more. We are giving some lower bounds against some kind of isolation scheme. So the paper, all in all, I think is 50 pages or more, and we just crammed everything in there that we know about the topic, maybe a little bit too much. But these two highlights, I think that they really show what interesting things can be done in this topic. Good. So let me say a little bit more about specific corollary of what we do. So this is one thing that we actually were able to de-randomize using our techniques. So imagine that you've got some class of graphs that admits balanced separator of size square root n. So whenever you've got a hereditary whenever you've got a graph from your class, you can always break it in a balanced way using square root and vertex. So in parts that are of size at most half of the original vertex. Yeah. So for instance, in planar graphs, you've got the classic Lipton-Tarjan separator theorem that tells you that, that there is always a balanced separator of size square root. Yeah. Then by appropriately adjusting our techniques, we can make an isolation scheme for the Hamiltonian cycles in such graphs that uses square root and random bits. Yeah. So actually pretty small number. Yeah. And then a corollary of this result is that we can actually de-randomize using going through the whole probabilistic space a previous algorithm for the Hamiltonian cycle on such graphs. Yeah. So as a corollary, we get the Hamiltonian cycle on graphs from C. Yes. So say on planar graphs, for instance, can be solved in 2 to the square root n time, in polynomial space, and deterministically. All these three conditions joined. Yeah. So previous approaches, the classic approaches, they did not focus on the space complexity. However, on WG last year, we made a polynomial space algorithm of this kind. So running time to the square root n and polynomial space using some tricks connected to tree depth. However, this algorithm used the cut and count technique and therefore was randomized. And now using this theorem about the isolation scheme for Hamiltonian cycles, we can actually de-randomize this algorithm, so give a deterministic algorithm with this complexity, both time and space. Good. So this is the overview of the results. And now in the remaining time, I would like you to show you a highlight of the proof, some highlights of the proof. And in particular, I would like to prove to you the following statement, or sketch a proof of the following statement, that on graphs of path width at most t, I can make an isolation scheme for Hamiltonian cycles that uses this many random bits. So t log t times log n plus log square n. Yeah, so there are two relaxations with respect to the theorem that we have seen above. Yes, namely, I allow one more log t here, and I allow path width instead of tree width. Good. So we will at the very end argue a little bit how you avoid this these two assumptions. Yeah, and the main source of randomness that we will use in our proof will be the hashing lemma of Fredman combination semi-eddy, so FKS hashing. So this is a classic hashing technique, and it says the following. So imagine that we've got some numbers, a1 up to am, yes, that are somehow not very large. They're at most exponential in m. M is some number, yes, and they're pairwise different. So let me choose uniformly at random a prime number from the interval, say from 1 up to m to the 10. Yes, so polynomial in m. Yes, so this this P is pretty large, but it is still small compared to the range from which AI are taken. Yes. So then I can hash my numbers AI modulo my prime. Yeah. And hope for the best that actually, because they were different before and the prime is actually pretty large, the hashes will still be pretty different. And indeed, they are pairwise different, the hashes, with probability close to 1, bounded inverse polynomial in M from 1. Maybe for the sake of time, I will not go through the proof in details, but you can see the proof now. It is not very hard. Essentially, what you see is that because the differences between the numbers are bounded, are in this interval, they have small number of different prime factors. Yes. So all in all these differences between difference AI and AJ, they in total have at most say m cubed different prime factors in total. However, the total number of primes in our interval from 1 up to m to the 10, yes, by the prime number theorem is still very large. So with very large probability, our prime number P doesn't divide any difference between AI and AJ. And if it doesn't divide any difference, then these numbers modulo P must be pairwise distinct. Good. So this proves the FKS hashing lemma. Good. So now what is the idea? The idea is to start with a very simple isolation scheme that is actually completely deterministic. It uses 0 random bits, yes, but assigns super large weights, assigns exponential weights. And this is a very easy isolation lemma, isolation scheme. Namely, for every edge E, we assign a different identifier of this E. So we say that the edges are numbered 0, 1, 2, 3, up to m minus 1. And then our weight of an edge E, I will call this weighting scheme tau for trivial, yes, is simply 2 to the ID of this edge. Yeah. So this, if you look at this and you think for a while, you see that actually every subset of edges receives a different weight. Because if I look at the weight of a subset of edges, yes, and I look at it in binary, yeah, the ones in the binary encoding actually tell me exactly what are the edges that are in my subset. Yeah. So because every subset of edges receives a different weight, clearly any family is isolated. Yeah. So observe that now we've got super large weights, yes, but no randomness at all. But now we can try to take this tau and try to hash it using the FKS hashing lemma. Yeah. For instance, if we had only polynomially many Hamiltonian cycles in our graph, yes, then here I would have in my FKS hashing lemma, yes, I would have a polynomially many numbers AI up to AM. These are the weights of the Hamiltonian cycles. They are different because our trivial weighting function tau assigns them different weights. And then the FKS lemma would tell us that if we choose a random prime that is polynomial in the size of the graph, then these Hamiltonian cycles get still different weights after hashing modulo this prime, right? But of course, the problem is that the number of Hamiltonian cycles in the graph can be exponential. And we need to somehow deal with it. So instead of hashing tau modulo prime once, we will hash it iteratively through log n levels in some sense. So this is the main idea of the isolation scheme that we design, and the isolation scheme is now here. Yep. It is actually very simple. It doesn't look at all at the graph. It just samples some prime numbers and hashes this trivial isolation and weighting function tau according to those prime numbers. Yeah. So let me choose m to be pretty large. It is say 2 to the 100 t log t times n. Yeah. So this is polynomial in n and also exponential in t log t. Yeah. So we sample log n plus 1 random primes from this interval, from 1 up to m to the 10. Yes. And then what we do, we take when we want to compute the weight of an edge E, we take the weights according to our trivial weighting scheme, yes, hash them modulo those primes, and put those hashes at different magnitudes. Yeah, so I take the hash modulo p log n at the lowest possible magnitude. Then the hash modulo, the next prime number is multiplied by m, so that these two inside the binary encoding, they do not mix with each other, and so on and so on. So if you think of this as, say, m is a power of 2, then actually the binary encoding of our weight will look like this, that you will take the consecutive hashes, yes, consecutive hashes of tau, and you will put them on next to each other, concatenate those hashes in the binary encoding, in this way obtaining the weight function E. Yeah. So of course, because log m is exactly this t log t plus log n, yes, in order to sample one of those prime numbers, you need this many random bits, log m, so this number, yes, and in order to sample all of them, you need to multiply it by log n, and this is the total random number of random bits that you need. Yeah? And the bound on the number of weights being 2 to the number of random bits, you can also easily check. Yeah? Okay, so this is the whole isolation scheme. Take a bunch of primes at random, hash the trivial weighting scheme modulo those numbers, and concatenate the results in the final weighting function. So now what remains, and this is what I will try to sketch now, is that actually this works. That our function, weight function omega, isolates the family of Hamiltonian cycles in my graph with very large probability. Probability 1 minus 1 over polynomial. Actually, I will not really talk about the probability of error. I will not do the estimates. I will somehow silently assume that all the good events happen, and the probability error analysis is kind of straightforward but tedious. So I will try to skip it in the description. So the idea is to prove this claim sort of by induction. And we now need to understand what does it mean by induction. So by induction, first of all, we need to inductively define our final omega. And this can be very nicely done, namely let omega 0, the first weight function, be simply the first hash. Yeah, so the trivial weight function modulo p0. And then we define this hierarchy of the weight function where the previous one, the next one is obtained from the previous one by shifting it in the binary encoding by m. Yeah, so multiplying by m and then adding the next hash. Yeah, so this is like a Horner scheme of how you would actually calculate this omega. Yeah, so then you can easily see that omega, the final weight function, is simply omega log n. Yeah? So we have sort of finer and finer weight functions that incorporate more and more hashes in this way. And the idea is do induction on I to show that these consecutive weight functions, they actually isolate more and more in our graph. Okay, so we need to understand that we need to use the fact that that the graph has small path width. Yeah, so we've got this. You can imagine this graph as like a long sausage consisting of bags. Yeah, so you can even make it a little bit more sausage-like. Yes, to depict it better. And in this sausage, you've got consecutive sections of the sausage. Yes, which are bags. The bags are of size at most t. Yes, and well, the graph happens in between. I will not introduce formally what does it mean a graph of path width at most t. I hope that you all have seen this. The total number of bags can be bounded by twice the number of vertices. This is also standard. Good. So an interval in our sausage, in our graph, is just a set of consecutive bags. Yes. And the boundary of the interval are the last and the first bag. So you can think of an interval as sort of a mid segment of the sausage, yeah, which is boundaried from the rest of the sausage by the left bag and the right bag. Yes, and we are interested, the interval concerns what happens inside here. Yeah. Good. So now, if you think about dynamic programming for Hamiltonian cycle on graphs of bounded, say, path width now, well, we have already understood, we have already sketched before how a dynamic programming state looks like. So a configuration on such an interval I, yes, for this dynamic programming, essentially consists of a partition of our boundary, yes, I into V0, V1, and V2, V0, V1, and V2, which tells us what should be the what are the expected degrees of the vertices, expected number of edges of f incident to those vertices in a partial solution. Yeah, so for every such partition plus a matching on V1, yes, we have a configuration and then a partial solution, so a set of edges inside here, looking for instance like that, is compatible with a particular configuration if it realizes it like that. So there are some technical conditions. For instance, every vertex inside should be incident to exactly two vertices, to exactly two edges of my partial solution, and the matching should correspond how the vertices from the boundary are linked inside the partial solution. Yeah. So for a configuration C, I've got this set of solutions that are compatible with these configurations. And now comes the key idea. And this idea is not entirely ours. It is actually borrowed from a paper of Kalampali and Tavai about isolating shortest paths. The idea is to show that the if iteration in this chain of more and more refined isolating functions, so omega I, isolates all the families of those partial solutions for all intervals up to length 2 to the I. So whenever I'm looking at my interval, at some interval that is pretty short, of length at most 2 to the I, and I look at any particular configuration in this interval, and I look at partial solutions, possible realizations of this configuration inside my interval, then this family of partial solutions should be isolated by my weight functions omega I. Yeah. So this is the claim that will be pushed through induction. Yeah. Okay. So for the sake of time, maybe I will not give you the full proof. The base case essentially concerns graphs of bounded size, and then you can easily see that the FKS hashing does the job. The main point in the induction step is to actually observe that if you have an interval of length at most 2 to the I, this is an interval I, then you can break it into two intervals, I1 and I2, that are shorter. And you know from induction that the previous weight function omega I minus 1 already isolates the partial solutions in this interval and in this interval. And now the idea is that partial solutions in the whole interval are being glued from partial solutions from the left and from the right. Yes. And the main observation is that if I have a solution of minimum possible weight on the whole interval, it must be glued from a minimizer on the left and a minimizer on the right. Because if this was not a minimizer, I could replace it with another solution that would have even smaller weight. And therefore, if I look at the minimizers in this whole interval I with respect to the previous weighting function, then actually maybe there is not a unique minimizer, but the number of minimizers is small. The number of minimizers is bounded by the number of possible partitions of the configuration into a configuration on the left and on the right. So it has small size, and this additional hash modulo pi gives us a perturbation that, due to FKS lemma, provide us that with high probability we get a unique minimizer with respect to the next weight function. Okay, so this was pretty quick. I hope that you understood the gist of this argument. So the idea is to essentially go in log n steps, taking twice and twice larger intervals at a time and pushing this induction step there. So then there are possible extensions. How do you actually prove those stronger results I promised? If you want to have tree width instead of path width, you need to redefine what is an interval. And from an interval in a path decomposition, you think of, rather than about those intervals, you think about segments in a tree, and segments are simply subtrees with a boundary of size at most 2. So there might be some additional guys here, but this is the part that is actually highlighted. And then you can easily prove a lemma that every segment like that can be divided into at most 5 segments that are twice smaller. For instance, this segment I could find a centroid and divide it into 3 segments that are smaller, but now I have a segment with boundary of size 3, so I additionally divide here, and now you see 5 segments here that are twice smaller and are indeed have boundary at most 2. And then you replace intervals with segments, and the whole reasoning goes through. If you want to reduce this log t in the number of random bits, this is actually pretty non-trivial. So what we are doing, we are using the rank-based approach here to understand that we do not need to take care of all the 2 to the t log t configurations, but they are actually, you can reinterpret it in order to only see, look at the 2 to the t roughly configurations at the time. This is quite non-trivial, and it requires care how you actually apply this rank-based approach. And finally, if you want to go from Hamiltonian cycles to any MSO2 definable property, I hope that the way I described the proof for Hamiltonian cycles was generic enough so that you can see, if you know how to deal with MSO2 problems, that instead of looking at configurations for Hamiltonian cycles, I replace them simply by thinking about MSO2 types of particular boundaried graphs, and then if you just search and replace configuration by MSO2 type, the whole proof goes through in the same way. The fun fact about this 1 and 2 is that actually the isolation scheme is exactly the same. Yeah, you again sample some random price of particular magnitude, you compute hashes, smash them together, and this is your final weight. It's just that the proof differs when it comes to proving that this actually works. Okay, sorry for being slightly longer than expected, but I guess I will end here. So thanks a lot for attention.
Okay, so maybe in 3, 2, 1 we can thank Michał by applauding. So 3, 2, 1. And if there are any questions, then probably it's the best time for the questions or remarks, which should be recorded, but we can have like a session of unrecorded questions later.
I have a question.
Yes.
In this application to the Hamiltonian cycles and other problems which you solve via cut and count, you could use, instead of isolation lemma, you could also use
Schwarzschild.
Yes, exactly, Schwarzschild. So is there any hope for similar kind of partial derandomization via this Schwarzschild approach?
Good question. I have no idea. We did not think about it. We were very much focused on isolation lemma, I must say.
Mm-hmm.
Yeah, it would require some thinking. What would actually mean a partial isolation? Well, yeah, you can just reduce the number of random bits or
yes, that's
drawing your. Yeah, good question. We did not think about it at all.
Mm-hmm. Mm-hmm. Yeah. Okay.
I want to ask that you mentioned that in the original isolation lemma, you can reduce the number of random bits from n log n to n.
Yeah.
So is it some simple observation that provides that?
No, it's,
so what's
it's
the idea
actually
behind this?
it's a paper from 80s of Chari et al. I'm not sure now. Maybe Carol can help me because he was doing a lot of literature research around this topic. It is actually pretty non-trivial how to do it. But in general, the general thing is that if you want to, if you have a universe of size n, and you have some family f that you would like to, like, you don't know it, but you would like it to isolate, then what you need to, how many random bits you need? I think you need log n plus the log of the size of f. So the smaller families you actually are concerned about, the less bits you need to use. But in general, the number of Hamiltonian cycles, let's say in an vertex graph, can be as large as 2 to the n or something like that. Or the number of the size of a family of subsets of a universe of size n can be as large as 2 to the n. So, and there are information theoretic lower bounds showing that you cannot do better.
Okay, second question, that actually what you do in isolation lemma is a stronger property than you need. You would need to have at least like one bucket of weight sums in which you get an odd number of sets.
Yeah.
So do you think that have you like tried looking at this property, or do you think that estimating a probability of such property is roughly the same as getting the original isolation lemma?
So the question is whether it would be simpler or like whether you could reduce the randomness by only insisting odd instead of equal to 1.
Yeah.
Yes?
Yeah.
I have no idea. I did not see any proof where actually they would use odd instead of 1, and I don't see how the current proofs could actually benefit from this odd. So maybe yes, but I don't think that I have seen any work like that. Yeah.
Okay, thanks.